All right, so I guess we can start. Okay, I'm very happy to have Doron Puder today. He's giving us 2 lectures, 2 hours this week, 2 hours next week. So teaching us a little bit about spectral gaps and combinatorial group theory, I guess, on which he's an expert. And then, okay, go ahead.
Thanks, Cayley. It's great to be here. It's good here. I mean, I'm here. Oh dear. So this should be. So I have 4 hours. So it's going to be. I have a lot of time. So it's supposed to be very gentle today, even more than next week. So this is joint work with Gil Alon from the Open University of Israel. And today, the first hour or so, I will mostly explain about the original Aldous conjecture about spectral gaps, which is related to the symmetric group. And then in the second hour, I think I will go through. I want you to go through we had a very interesting process of investigation or starting to understand what is the possible analog. And I want you to go through it with me a bit. So I'm not sure it's the most, I just want to tell the story of how.
It's a cynical.
Hmm?
You're giving us the cynical, not the highway.
Yes, exactly, yeah. Yeah, and next week, I plan to give ideas from the proof, we'll see some representation theory and so on. And
Maybe one more comment. This week, Alex Lubotsky will be visiting. And on Thursday, he's giving a first talk at the What Is seminar. He's going to talk about property tau, which I don't know, might fit into you.
And the talk is at 11:30 or?
It's at 11:30 here. Okay.
okay, so I'll start with the original. So the first part of this hour, this hour should be about the original conjecture, I guess then. And I want to present, there are 3 points of views. All of them are going to be important afterwards. And I want to start with the first one. So first point of view. Which is Cayley graphs versus Schreier graphs. Okay, so here is the setting. The setting is that we are in the symmetric group on as elements, and there is a subset S, a subset of all the transpositions. And we compare, okay, so let's go to the other this board. So we have on the one hand we have the Cayley graph. Respect to S. And on the other hand, we have the Schreier graph, which I will explain what it is, which depicts the action of the symmetric group on the elements 1 to n, again with respect to S. Okay, so let me define briefly. The Cayley graph is just a graph with vertices. So there are n factorial vertices, which are identified with the elements of the group. And we put an edge whenever we have any sigma in Sn. And sigma times S. We have an edge for every sigma S in the symmetric group, and S in our generated set, in our set. Okay, so this is the graph. I will soon draw in a particular example. In the Schreier graph, this is n vertices, 1 to n. And we put an edge from I to j. whenever for every if sigma, sorry, S of I with J. Okay, so whenever S takes I to J, we put an edge between I and J, and we may have loops. So in general, I mean, if S is so basically for like that.
You mean there exists little s in big S that takes
Yeah, not that I want to have multiplicities
Hmm.
in general, so I don't want to write it like that. So let's say, I mean, so if I just have, let's say, if the edges that come from IJ, so if this is my graph, 1, 2, I, J, N, so I will have one edge here between I and J, and loops in all the other ones. Okay, because IJ takes 1 to 1 and so on. And these loops have like weight 1, not 2. Because
So
yeah,
will you care about these graphs when they're not transpositions? Like, will you need directions or something?
I mean, so for now, it's only transpositions. In general, I will want my subsets to be symmetric. So S is equal. I mean, if any element is here, also its inverse is here. So I will not care about orientations. Okay, so here there are. So now I want to. So the spectrum. We consider the spectrum of the adjacent symmetrics of the Cayley graph. So we have lambda 1, lambda 2. These are all real eigenvalues, and they are n factorial of them. And the first one is always just the degree. This is a regular graph. The first one is the degree of the graph, which is the side of S. And here we have n eigenvalues. Perhaps I'll use different letter. And again, the first one is the degree, which is the same, it's S. And so I want to continue the comparison. So here's one observation that the spectrum of the Cayley graph contains the spectrum of the Schreier graph. Okay, and why is that? Because, I mean, so the proof, we just take any, if F is an eigenvector of the Schreier graph. So we have a value for every vertex, right? We can lift it to let's call it F, which is defined on the symmetrical, on the whole symmetrical by. So let's say that I put on the value sigma, I put F of sigma equals of 1. So there is a very simple procedure to lift the function that I have on n vertices to a function on n factorial vertices, and it will have the same. It will be an eigenvector with the same eigenvalue. Okay, and now I want to show you. Let's look at an example. We'll all be clear for an example. So let's take S to be 1, 2, and 2, 3, and n equals 3. Okay, so let's start with the other side. So what does the graph looks like? So we have 1, 2, and 3. These are the edges that correspond to 1, 2, and these are the edges corresponding to 2, 3, okay. What are the eigenvalues? So let's see, so we have, okay, first of all, we have a trivial eigenvalue. Okay, the eigenvalue. Okay, if I put 1 here on every vertex, you see, then, I mean, when I apply what does the adjusted symmetrics do? What does it do? It replaces the element here with the endpoints of the edges, right? So here, instead of 1, I collect 1 from this loop and 1 from this vertex, so I get eigenvalue of 2. Another eigenvalue is this one. So this is eigenfunction, this one. So you can see that here I get 1, and after I collect the value of the neighbors, I get 1 again. Here it's 0, I get 0, and here it's -1, I get -1, so the eigenvalue is 1. And the last one is this one. So here the value is -2, but when I collect the neighbors, I get 2. So yeah, so the eigenvalue is -1. Okay, is this clear? Just computation. And you can check it. Okay, now let's see what happens here. So first, let's draw the Cayley graph. So first, let's draw it here. So here I have 3 factorial, so 6 vertices. I draw it on a circle. So this is the identity. 1, 2. 1, 2, 3. And these are the edges correspond to 1, 2. And these are the edges correspond to to 3. And let's look at the eigenvalues. So first of all, I want to try to do what I did before. I want to lift these eigenvalues here. Okay, here it's this eigenvalue. Just get 1 everywhere, and you see it's still 2. So this is eigenfunction. You get 2. Now, if I want to, I just want to show you how to lift this one, and then I will complete the other details faster. So I get 1 for every permutation that maps 1 where 1 is a fixed point. So I get 1 in these 2. I get 0 whenever 2 is mapped to 1. So 2 is mapped to 1 here and here. And I get -1 in the remaining ones. And as you can see, the eigenvalue here is again, if I replace each value by the neighbors, by the 2 neighbors, I get the same value. So the eigenvalue is 1. Okay, so I can continue like that. Okay, perhaps I will skip I don't want to do the whole computation, but so if you do the computation, you see that the spectrum is -2, -1. Okay, this is the spectrum. Okay, so far we only had some computations. We didn't have any conjecture. But it also,
Is there anything like homomorphism from the Schur graph to the Cayley graph?
so the Cayley graph, there is a morphism from the Cayley graph, morphism of graphs, a covering morphism from the Cayley graph to the Schur graph.
Oh, I'm asking. Oh, I see.
So there is a.
So you can pull back eigenfunctions along it. That's the separation.
This is what this is. You follow this procedure. I mean, you can always draw the Schur graph and then the Cayley graph in a way that it's a covering space, very nice. And then Yeah, but they don't want to. Yeah,
Did we get lucky that the eigenvalues were all integers, or is that something special?
no, we're just, okay, so I should say, I mean, I wanted to have a small example, but it's very misleading. I mean, it doesn't seem like that big of a difference, but remember, I mean, n is only 3, so this is, we have only, n is half of n factorial when n is 3, and yeah, it's completely misleading.
Okay.
So it's not always integers also. Okay, so the first, I think, with the first time that people notice that something interesting is happening is in the work of the economists of Shafani. So they were interested in card shuffling. So they asked, I mean, you have a deck of cards, and at each step, you pick at random 2 cards and swap them. And they asked how fast, in how many steps does it take the deck to be fully mixed or very close to fully mixed? And an important step in the way was to actually compare these 2 processes when yeah, okay. So perhaps sorry, before that. Yeah, before that, I just want to, I forgot to mention. So we have this observation. So the corollary from that, from this observation is that, right, I mean, this spectrum is contained in the other one. So mu2 is at least, it can be larger than lambda2, right? So it follows from the following, from the previous observation that that mu2 is at least lambda2, right? So in other words, the spectral gap of this process can only be larger, equal or larger than the other one. This just follows immediately from the previous observation. And then the equation of Shafani. So again, it's part of the work on card shuffling. They show that if S is the whole set of transpositions, then these 2, the spectral gaps are identical. And then there were other special cases, I think there were other examples of such graphs where the same phenomenon happened, and then Aldous conjectured in 1992 that the same is true for any set of transpositions. Okay, and you see, by the way, so in the example we saw that, right? I mean, okay, you have to believe me that this computation is, I didn't show you what is full spectrum, but it's easy to compute it. You see the second eigenvalue here is 1, and also here it's 1.
So should S span the entire group or not necessarily?
Okay, so what happens if it doesn't? So if it doesn't generate the whole group, so a set of transposition generates the whole group if and only if the graph, you can think about the graph on n-vertices where you put an edge for every, basically this graph without the loops.
The smaller set.
Yeah, so I'm basically this graph without the loop, so it generates the group if and only if this graph is connected, right? And so if it doesn't generate, this graph is disconnected, so the second eigenvalue, there's no gap. And of course, this one is also disconnected in this case, and then there's no gap. So, I mean, it's still true in a...
Oh, but then you can say it's true even further down.
Yeah, right, it's true by induction, yeah. Yeah, it's true. Yeah, it would...
The second.
Yeah, it should be true also, yeah.
Second eigenvalues would be the same just because they will be the same as the maximal, right?
Yeah, this is how usually how I think about it, but probably you can also say something about the first not to Okay,
So this is just like people saw a bunch of cases and they thought, like, did people have also a reason to?
I mean, I'm not sure.
That's how, that's how people.
I mean, I think Aldous had many, it's not his only conjecture. I think he has a very good intuition for these things, but I don't know. I don't know how, I'm not sure what it is based on, but, so it's a very broad conjecture. I mean, you see, there is, so you should, again, we compare here a spectrum of n factorial with n factorial eigenvalues. And it says that in a large set of cases, family of cases, deterministically, it is the second eigenvalue comes from a very, very small process of small pool of only n eigenvalues.
Like what you said before about like connectivity, right? This is
Yeah.
saying that if the group is transitive, then it is also generating, right? That's like if the
Only when it's generated by transpositions.
right. I mean, that's what if you're looking at the transpositions, once they're transitive, their action is transitive, then they're generating. So
Yeah.
is this kind of like a robustification of this phenomenon?
Yes, and you can say, perhaps I will talk about it a bit, what happens. I will talk briefly about what happens when you take other generating sets and whether this can be generalized, what you're referring to. Okay, so before I move, so first of all, I mean, this conjecture was proven. I will say about it, I will talk about it soon. But first before we do that, I want to, this was the first point of view. I want to describe the other two. So the second point of view is the interchange process versus the random walk. So I think this is probably how the original conjecture was stated. So another way to think about it is that you take a graph on n vertices, and you put an edge ij if and only if ij is in S. So again, we have a subset of transpositions, but we just think of them as edges in the graph on n vertices. And then we have, on the one hand, we have the interchange process. On the other hand, we have random walk. So how does it work? We have the graph. So let's take our graph as before. So we take the same, in the same example we had before. So in the interchange process, we have three different particles. So three distinct particles. And what we do in every step we choose one of the edges at random. And then we swap the two particles that sit at the endpoints of the edges. This is called the interchange process. So again, this is in general, when we have n vertices, this is a process this is a Markov process with n factorial states. And we look at the adjacency matrix of this process, and we have a spectrum. This is really this is the same as the Cayley graph. It's just it's really the same story. It's exactly the same definition, just in different language. And here, so we compare it with the random walk, where we have only one particle. So let's choose, let's say the red one. So we have only one particle, and and what we do is, again, we choose at random an edge. If we choose this edge and the particle is not here, we do nothing. And if we choose an edge who is adjacent to the vertex where the particle is, we move the particle to the other side. Okay, so again, we have n states, there are n eigenvalues, and again, the conjecture is in this, that the second eigenvalue of the interchange process is the same as the second eigenvalue, of course, mu2 of the random walk.
So really the picture is that there's one graph, and either you are tracking one particle on this graph, or you're tracking a different particle on every vertex on this graph.
Yes,
What's happening to all of them?
yeah. Yeah, and the conjecture is that the spectral gap is the same in both processes. Yeah. Okay, so this was the second one. The third one is the one that I like the most, and it's the one that will be most useful for us. So third point of view is representation theory. Or full representation theory. Okay, so here I want to give a crash course of 3 minutes on representation theory of groups. Okay, so so I will do it for I'll talk about finite groups, but so now G is a finite group, and S is any subset of the group which is symmetric. So okay, so this means that every element in S, if an element is in S, then X inverse is also in S. So it's symmetric, and once again, okay. So the point is that that's too so high for me. So again, we consider the Cayley graph of G with respect to S, and we look at the adjacency matrix. So this is, and we notice that. So notice that the adjacency matrix is the sum over all the elements in S of what I would call the regular representation of S. And what is the regular representation of S? So I just taken a matrix which is whose indices are the elements of the group. So G1, G2, and so on. And this is a permutation matrix which depicts the multiplication by S from the right. Okay, so if I have here an element G, I would choose, I look here for the element GS and I put 1 here. Okay, and H, let's say this is HS, I put 1 here, so on. This is going to be a permutation matrix. And just by definition, the adjacency matrix of the Cayley graph is the sum of these matrices over all the elements. Now this is, so like from the group 2. This is one example of representation, a linear representation of G. In general, representation is, so this is a homomorphism, group homomorphism from G to GLDC, some to GLDC to a space of matrices over the complex numbers with some dimension, and for us we always define a dimension. And here. And we think of representations as equivalent up to a change of basis. Okay, and equivalence. So we said that rho one is equivalent to rho two if it's same up to a change of basis. And okay, we have another notion which is the sum. So if we have two representations from GLD1 and rho two from GLD2, we have the sum of them, or the direct sum, is going to be okay. We take G into the matrix, block matrix, where we put here rho one of G, here rho two of G. Okay, so this is the direct sum of representations, and we say that the representation is called irreducible if it is not equivalent to a sum. Okay, so let's see one example. Anyway, okay, we'll call it an irred in this case. Irreducible representation, we'll call it an irred. Okay, in this top.
Irrep or irrelevant this?
No, irreducible representation.
Ah,
So yeah. Okay, so here's an example. You can take the, okay, I'm not going to call it the standard, but we can take the representation of Sn to GLN by just taking sigma to the permutation matrix. Okay, this is so I take any permutation to the permutation matrix. So this is, it's not irreducible, it's reducible. So in fact, you can see that rho is equivalent to rho one plus rho two. Well, rho one. So so I just say that V say V1 is just the span of the all1 vectors, and you see that, I mean, this is a vector which is invariant under any permutation, right? And let's say that V2 is the orthogonal subspace. So this is a space of all vectors whose sum of coordinates is 0. And it turns out that if I'm going to write this representation in this basis, so I choose this element, this basis element, and n-1 basis elements which span this space, I will get exactly this structure of block diagonal matrix. Okay, so, and by the way, this is going to be, in this case, rho one over this space. The action on this is just, it does nothing, right? So this is called trivial representation. And this one is called, I will call it the standard representation. So it's n-1 dimensional. Okay, and they are both irreducible in this case. Okay, so, and this clear? Okay, so what do you
I
want?
have to see what the standard is irreducible or.
Okay, so to show, yeah, it's not hard to show it, something is reducible. Okay, so if you have this structure, right, what you can see is that if there are some non-zero vectors where, let's say you take this. If I take, for example, a vector like that, and I act by all the elements of the group, and I take linear combinations, I will never get to any non-zero element in the upper side. And this is the criterion you can use. So you can show that for any vector, non-zero vector you start with, you can get to any other vector using the elements of the group and linear combination. Okay, so yeah, and then it's a simple exercise to show that this is the answer.
Sorry, what was the criterion again? What did you say?
So you can take, you can show that from any vector, you can basically, any non-zero vector, you can get to any other non-zero vector by applying the elements of the group and taking linear combinations of, and closing with the linear combination. Okay, so before I say the conjecture in this language, so I want, yeah, so some facts about S. So for any group, so this is a basic fact from representation theory of finite groups. The regular representation. So this again, this regular representation, this is of dimension the same as the size of G. It is very reducible, and in fact, it contains all the irreducible representations. So this is equivalent to the sum over all irreducible representations of G. In particular, there are finitely many equivalence classes of irreducible representations. And each one of them, the multiplicity, it appears, the number of times it appears in this decomposition is the same as the dimension. This is true in every group. And another fact which we won't really use, but just I think it's good to remember that, or to remind that in Sn, so irefs of Sn are in one-to-one correspondence with partitions of N or with Young diagrams. On N squares. So, for example, I mean, this is the picture you need. I mean, we don't really need it. So this is a Young diagram. It has 9 squares. So this represents an irreducible representation of S9. And in this language, and in this language, the trivial representation of Sn is this, and the standard is this. Okay, so I need overall n boxes in each of them.
Oh, any intuition on what the rows and columns in the Young diagrams mean?
No, it's too complicated to. Yeah, I'm not sure I have intuition. Like, there's a long explanation that I can give. I don't know if there's anyone who can give a short explanation. I'm not sure, but yeah, I'll say. I mean, what do you think? I mean, you could mistakenly think that. I mean, these are partitions of N. They correspond to conjugacy classes of the symmetric group, right? The conjugacy classes are just the cycle structure, are determined by the cycle structure of the permutation, and you can think of it as a partition. So you have one cycle of size 4, one cycle of size 3, one cycle of size 2, and it's again a general effect that the number of irreducible representation group is the same as the number of conjugacy classes, but it is, but the symmetric group is a very special group in that there is some kind of a bijection between conjugacy classes and representation. This is usually not the case, and even this bijection is very complicated. I mean, why? I mean, why again? Why these diagrams represent irreducible representations? Okay, so and perhaps one more fact in a Cayley graph. So we always have what is the eigenvalue of okay, so if we use this, so now I want to use this, so what happens? So if you look at so if I take this fact together with what we said before, so we see that after a change of basis, and this is again true for any group, if we look at the adjacency matrix of the Cayley graph, we said that this is the sum of the regular representation, but I can use this fact and then get a block structure. Then I get that this is the sum over S in S, and then I get a matrix, which is a block diagonal matrix, where in each block we get some representation of S. Okay, and you see, so and now we want to understand the spectrum of this sum of matrices, and now it's obvious that the spectrum, each eigenvalue comes from one of the irreducible representations. Okay, so each eigenvalue of the Cayley graph comes from some irregular. And as an example, what does the trivial?
Is this just like a Cayley graph is sum of a regular representation, but with a change of basis, so that it becomes like a direct product of errors?
Direct sum, yeah.
There's some.
Yeah. So I could, yeah. Yeah, you know, before I'm actually expecting, let's just see what you got. Keep using charts.
Yeah, that's okay. So maybe just, if you were completely formal, instead of writing the adjacency matrix, you would conjugate it by a basis change, and then it will equal this.
Yeah, and the point is, I mean, so this is an important point. In each one, for any element of the group, I will get the same decomposition with the same blocks.
Yeah.
The same structure, not the same element, not the same content of the blocks, but the same structure. And that, so it is.
Otherwise, this wouldn't be a value.
Yeah. Yeah. So perhaps before I'll say the other thing, so in our example, we had, so if G is S3, the symmetrical group on three elements.
Use a different color.
Yes. So if G is a symmetrical group on three elements, so instead of, we had the Cayley graph is, I mean, the adjacency matrix of the Cayley graph is 6x6 matrix, but if I use this change of basis, so in a symmetric group, we have three representations. We have three Young diagrams. We have the trivial representation. It just takes every element, this is a one-dimensional. Takes every element to one, to the matrix one, to the one by one matrix with the content one. This is the standard one, the n-1 dimensional. This is the same one. This one. And what is the third one? It's again one dimensional. This is two dimensional. And we have the sign, which is again one dimensional, and it maps every element, every permutation to its sign. And the adjacency matrix in this case is equivalent conjugate to to this matrix, well, here we have trivial. Here we have two copies of standard, and we have one copy of the sum. Okay, again, the number of copies is the same as the dimension. Okay, and in general, what happens here? What is the eigenvalue here? It's one for every generator, and the sum is just S. Okay, so the eigenvalue corresponding to the trivial representation is lambda 1, which is the size of S. Okay, and then so in this language, what is Aldous conjecture? Right, it says that the Schreier graph we had is exactly this representation. Okay, the Schreier graph we depicted before, the adjacency matrix is exactly this one, where we take any element, in our case, transposition, and we look at the permutation matrix. So it has one on the diagonal, except for I and J, where we have right I and J. It's mapped to this one. Okay. And we said, and here we see the trivial eigenvalue, which is lambda 1, and the standard. And so in this language, Aldous conjecture is that if S is again a subset of transpositions, then the second eigenvalue always comes from the standard. So again, this n-1 dimensional permutation. Okay, but so again, and mind you, this is this one. From this explanation. Okay, so far so good. Okay.
Do you know how special the standard representation is? So for instance, I can take the representation on n choose 2 elements. Do you know something similar is true, or what do the eigenvalues look like on these other canonical representations?
So you mean the irreducible one or the?
Not the reducible one, just the n choose 2 elements.
So it will contain the standard. So you will see it will
Right.
still. So basically, if you take any one of these, like a intermediate thing between the Schreier graph and the symmetric group and the Cayley graph, and they will all have the same spectral graph. But if this conjecture is true, which it is.
Also, do you know how the other eigenvalues behave? Like you get more and more matching of eigenvalues as you go up this.
If I get
Like the third eigenvalues will be matched and then like a.
I don't think so. No, I mean I don't think there is a. No, it's really a phenomenon of the second eigenvalue.
I see.
Because also lambda 2 would show up with multiplicity on the.
Yeah, right. So you see, basically, you see from here that lambda 2 appears with the same multiplicity as the multiplicity of at least the same multiplicity as the multiplicity of this dimension of this representation. So you'll see it with multiplicity n-1 at least. And by the way, we saw it in the example. With n equals 3, we saw multiplicity of 2 of the second eigenvalue, which was 1. So it was not a coincidence. It's always the case that you get multiplicity at least n-1. Yeah, okay. So before I want to finish with this hour with some words about the relation. First, I want to state that. So, what happened after? So I told you this was proven. This is no longer a conjecture. I just want to mention So there were many, so between 1992 and 2010, which is when this was proven, there were some partial results. I want to mention just one of them because so Johnny and June Race. They proved it for trees. So trees, I mean, now I'm thinking about the second approach where I have a graph. So whenever the graph that I get from this set of transpositions is a tree, the conjecture is true, and they really used the second approach of looking at it as a graph and a process. But then I think there were other special cases, but eventually in 2010, so Caputo, Liggett and Richthammer. This was 2010. It appeared in jumps, so they proved the conjecture. And I can say they used mostly the third, actually, representation theory. At least the way I see the proof, mostly representation theory. And I want to mention that they even showed it for and they showed it even true for they proved it even for weight, more general version where they have weighted graphs. So weighted graph means that I take a set of transpositions, but with some non-negative weights to each transposition. And when I take so remember in the original thing, we pick at random an edge, so I can pick it with any probability distribution or any distribution. Right, so I take any distribution on my edges, and I do the same process, and I get this same equality of spectral gaps. And okay, so my next week is not fully planned yet, but I may give the outline of the proof of this. It's very nice.
So what's so special about transposition?
Right, yeah, it's a good question. So I want to say some. I mean, basically, okay, perhaps I will. I mean, first of all, it's not true in general, but it's a good question. I mean, what is the most general regime where this holds? But why transpositions are special? I think one way to think about it is that they are very close to the identity. I mean, it's the permutation that's closest to the identity. And perhaps, I mean, you see, if you think about the random walk, so in this model, right? So it's a very, very lazy walk, right? So it means that the eigenvalue, the largest eigenvalue is very close to 1 in a sense, because most of the times you do nothing to the particle. So it means that the largest eigenvalue here that you get is going to be very close to 1, which means that perhaps it gives you some intuition why you expect that in between the n factorial eigenvalues to be close to.
But that's
1.
just for one transposition. You have a set of.
Yeah, but still in every step. So imagine I have a graph on a graph on vertices. At every step, I choose one edge at random. And then if my particle doesn't happen to be here, I do nothing. So it's a very lazy walk. So you can think about the eigenvalue is very close to 1. So it's a very lazy walk. The second eigenvalue.
Is that true for other reflection groups?
Yes. Okay, but okay. So perhaps I should. Yeah. So let me be more. Yeah, I wanted to say a few words about it. I think it will answer your question as well. So, the general question is generalizations, right? And I think I can, in a crude way, I can divide this possible generalization to three types of generalizations. One is other sets in Sn. One is other groups. And the third one is other processes. So other processes, I mean, that I look at the graph and I just look at the graphs and the processes on the graphs with, perhaps now perhaps I have instead of one particle, I have two particles which are identical or non-identical. And there are many options of processes that you can define. So let me go by them one on one. So first of all, other sets in Sn. So again, like I mentioned before, and I think it refers to some of the questions here. This is not true in general, not true for arbitrary. For arbitrary subsets, and perhaps the simplest example is let's take just a full cycle and its inverse. So why is this a counterexample? Because
Graph will be disconnected.
yeah, exactly. So this doesn't generate the Cayley graph. So the Cayley graph, if I take this generating set, I just get the Cayley graph is just many cycles. There's a lot of cycles. It's disconnected, so lambda 2 of the Cayley graph is just lambda 1. But the Schreier graph is connected. It's a cycle. It's one cycle. So mu2 is strictly less than mu1. Okay, you can say that this is cheating. What if I take generating sets or so there are some attempts to there are some generalizations. So there are some generalizations. I would call them generalizations. Let's call them modest. Okay, so there is no. I will mention one conjecture that is probably true, and we don't know if it holds. I will mention it in the next hour. But there's nothing very exciting, too exciting here. It's just not that it's known.
Is there a counterexample when S is generating?
Yes, yeah. So you can take, for example, okay, what's the smallest one you know? The smallest generating set?
One transposition in this thing.
Yeah. One transposition, which is? What? Yeah, no, I gave this as a question in one of my exams in group theory.
I think this was on my group theory exam 10 years ago.
Oh, nice.
You can use any transposition, right?
No, I mean, if you take here, if the difference, if 2 is not immediately after here, if it's not disjoint from N, then it doesn't generate. Yeah, you can take any transposition. But anyway, if you take this one, for example, then the second eigenvalue doesn't come from the standard representation. It comes from, I think it comes from this one. And yeah. But it's also not true. I mean, you can also show that you can actually beat any irreducible representation. You can show that basically you can get any, you can construct your set in a way that will give you so that the largest eigenvalue will be in any irreducible representation, basically. So there is no completely general statement, which is very clean.
For random sets?
Yeah, that's a good question. Good question. Yeah, then it could be that, yeah, I would imagine that it might be true for random, but I mean, I could believe that it might be true, but it's very hard to prove this. Okay, so what about other groups? So up to, I mean, so there are, again, I would say modest generalizations with relatives, with cousins of symmetric group. So like reflection group, you can think about, for example, sign representations. So it's sign permutations. On the group of sign permutations, there is some phenomenon like that, okay? And of course, I will talk today about generalizing to UN, but this will be in the second hour. And what about other processes? Here there are some results. I'm just not fully an expert on. This is very much what people in probability theory do, and I'm not as much. I think on top of everything that's done. So there are some nice generalizations there, but I'm not sure I know the entire picture there. Okay, let's see. So, yeah, so this was the introduction. This is what I want to say about the original conjecture, and the next hour I'll talk about unitary groups. Yeah, so let's take
2 minutes.
2 minutes, no, 7 minutes. Okay, so first of all, so again, what I'm going to do is roughly like go through roughly the same thought process we had. For us, it took us several months, but it'll be 1 hour here. But I want to show you that it's not obvious what to do. But first of all, okay, just so that we are on the same page, UN is just right, all the matrices such that the inverse of A is the same as the dagger. I mean, yesterday it was there was a cross here, and this is just by definition, this is the conjugate transpose. So the rows are an orthonormal basis. Now, so this is not a finite group. So the last hour I just talked about finite groups, but basically, because it's a compact group, and so all the irreducible representations and all the irreps are finite dimensional. So it's a very similar story, but there are infinitely many of them. Now, there is, and I will talk about it much more soon. Now, there is no really a Cayley graph, but there is an analog of a Cayley graph. So you can think of an analog of a Cayley graph. So you can think of a Cayley graph of a group. So it is an eigenfunction, some function on the vertices of a Cayley graph is like a function from the group to C or to R. So you can think about functions from the unitary group to C or R, but you have to, because you need to take some, I mean, you can't take any function, but basically you want to, basically you take, you look at the action of, let's say, an element in UN on space of function on Ln. On L2, where you act on. So if I have a map in L2 from UN to C, then A intersection on F, if I want to evaluate it at the matrix B, would just be F of A inverse B. So there is a way to do it, but I don't want to think in this way because, I mean, we'll just think about the irreducible representations, which is easier to work with and easier to understand. It's for me. But here are some basic questions. Okay, so we want to see if there is a. So we want to generalize Aldous to UN. So what do we need to do? First of all, what is the analog of transpositions? So which elements? And this should be the analog of transpositions. The second one is it's not clear what representation. Again, it's the analog of the standard representation then. And perhaps another question, which I'll just put in is how to check or how to simulate or check. Let's say to simulate. So so first of all, how do we simulate? First of all, there are infinitely many representations, so I can't let the computer check everything. But what I want to do, I mean, you see, this is a very strong phenomenon. I could have recovered the Aldous phenomenon in symmetrical by just comparing several irreducible representations and only seeing that one of them always dominates the other. And this I can also do here, at least in simulations, right? So I can simulate just some representations and look for this kind of domination, that the largest eigenvalue here is always greater than the largest eigenvalue of this in a deterministic way. And there's another question of, this is, yeah, okay. Okay, so we'll talk about it more. So let's start with, so first of all, which elements? Okay, so the first guess that we had was, okay, we want something that's close to transpositions. So remember that a transposition is very close to the identity. What do I mean? I mean that if I look at the, let's say the identity minus if you look at the identity matrix minus the permutation matrix, it corresponds to a transposition. Okay, let's take this transposition. What I get is and everything else is 0. This is rank 1. Okay, so the first guess was to imitate this behavior and think about transvections. So a transvection is just A in UN such that the rank of I minus A is 1. Okay, this means, in other words, these are unitary matrices which up to conjugation have this form. If up to conjugation, they have one eigenvalue which is not 1, and the other ones are 1. And lambda is on the unit circle. Okay, so this is a nice conjecture, but it doesn't. I mean, it doesn't work, okay? So just doesn't work by simulations. So this didn't work. This was like 10 years ago, I think, or.
Do they even generate?
So I think, yeah, if you take all the transpositions, yeah, I think they should generate, yeah.
Because I would say like quantum gates should be easier things that generate you.
Yes, like they do generate.
No, somehow it doesn't.
Not if you fix a finite set, they can't generate everything, but they could. Most generate a dense subset, but if you take, but this set is infinite, so I think if you take.
Because you allow basis changes.
Yes, yeah. So if you allow, yeah, so
Not
basically,
fixed to like a standard basis of qubits or something.
at least in this guess, no.
Oh,
But soon, yeah, soon you'll be right.
Why don't you just take the transposition, like a sign transposition, like this 1 minus 1 minus 1 1 thing?
So just -1 here. Like this.
Oh no, like not even allowing basis change, like not just.
Yeah, okay. I mean, first of all, if I just conjugate, I mean, then the eigenvalues are the same, so it doesn't really. Well, okay. So you're saying just look at these methods.
Yeah, like the.
Yeah, no. So it doesn't work. I mean, yeah, I'm pretty sure it doesn't work. It also. It will only generate a very small subgroup inside, so it's not.
No, if you allow signs, like not just one, like any complex unit number, it doesn't generate.
What do you mean?
Like you replace every one with any complex unit number.
You mean each of these ones?
Yeah, like e to the IC.
Yeah, then they would, no, then it will still just generate, I mean, if you fix the basis, so with the same basis now, it will generate only the group of permutation matrices where you allow.
Every unitary is conjugate to such a matrix, so clearly.
No, but if you fix the basis, it depends.
Yeah, I'm saying that.
Yeah, if you fix the basis, you just get a matrix of permutation matrices, but instead of ones, you allow any element on the unit circle.
When you say it doesn't work, what do you observe?
So we just simulated some of the representation and we saw that there is no deterministic phenomenon. So we looked at some representation of, okay, we didn't check all of them, but yeah. So I will soon describe the representations of UN and then I will, but just we didn't see anything deterministic. Nothing that looks like.
Doron, does it make sense to measure closeness to the identity by another measure, like not rank? This is very rigid, right? Very discrete, but like maybe think.
Yeah, but so maybe, but yeah, we didn't come up with something, but there might be. Okay, so this just doesn't work. I mean, I would say it doesn't work. It doesn't show any striking results in simulations. Okay, so then basically, I mean, this was quite a few years ago, and then we worked on other stuff. And then we returned to this question, and then we had this, still remember this day, we had this revelation. It's very simple, but I mean, like we already knew for several years the following observation, but we never thought about it in this context. So it's a very simple observation about the symmetric group, which is that so I would say that Aldous conjecture for S, which is, let's say, so I take any subset of transpositions is equivalent to the same conjecture for. So I want to, instead of taking a transposition, I want to take a lazy transposition. Okay, so what does it mean? I mean, in practice, if you think about the graphs, for example, okay, I erased all of the graphs, but it just means that, again, in every, I have a graph, I have edges, in every step I choose an edge, but then with probability 1/2, I use this edge and do what I did before, and probability 1/2, I do nothing. So it's like a lazy version, but this laziness, it just, it takes the spectrum of every irreducible representation, of all the representations, and it shifts them by some affine transformation. So it's the same shift on all the spectra of all the processes. So if the spectral gap was the same before, it will still be the same afterwards. I mean, you can actually say that the new λ2 is just λ2 plus 1/2. The old λ2 plus 1/2. Okay, but if you think about this, what is that? This means that instead of just looking at transpositions, what you look at is this equivalent to a copy of symmetrical on two elements. Right, so each of these elements, if you think about it as all the permutations, for example, if you take the transposition 1/2, and then now I think about it as either 1/2 or the identity, this is all the transpositions, all the permutations that have this form. There's ones here and something arbitrary in this minor.
Yeah, all the rest are zeros. All the rest are zeros.
Yeah, all the rest are zeros. Yeah.
I'm not sure I understand. So something specific in these 4 entries.
Yeah, but I'm saying I look at all the possible. I mean, basically, first of all, this is like a.
All these like convex combinations of 2 things.
No, I'm saying I take all the possible. I take an average over all the permutations that have this form where this is something.
Okay.
Okay, so in this case, only either 1/1 or 1/1 here, right? I mean, there are only 2 options, but I mean, it's like it's an embedding of. I mean, it's an embedding of symmetrical. Okay, I wrote it, but. In the symmetrical one n elements. And if you think about it like this, then there is a natural way to generalize it to the unitary. Right. Yeah, and okay, I should say that this observation, as I said, I mean, it wasn't new. It was the only new thing was to think about. To remember it when we think about unitary groups. So in fact, this was conjecture by Caputo. Okay. Yeah, so it was observed by Caputo already very shortly after they proved the original conjecture. So it appears in some PhD thesis of a student of Caputo. As I could this observation and slightly more. So what do we do in UN? So we take basically we take S is again a subset of all the pairs, and we take. So how do we sample a random element from UN? We take any probability solution on S. So basically, I mean, it doesn't matter. You can actually just take S to be equal to this because I allow probability distribution, so it can be 0, right? With some, so I take any probability distribution on S, and then take uniformly random element in U2. And embed in UN exactly the same way. So we have an element A, B, C, D in U2, right? So we map it to the element where I take the on the IJ coordinate, I see A, B, C, D, and the rest is ones and zero.
But you don't have anything about, I mean, sort of the really surprising thing about spectral gaps for unitary groups that you could create a spectral gap with finitely many elements. You don't have anything.
I don't have anything like that. Yeah, this is disappointing. Yeah.
Where are you using the probability distribution?
Hmm?
Where are you using the probability distribution?
So the probability, so I pick, I mean, there are two stages in this, the way I generate.
You embed U2 in UN, right? That's sort of what the distribution gives you.
I mean, if S was like an expander graph on N vertices, then the distribution would be to choose one of the edges in this expander graph and then put a U2 just to.
Yeah, but it doesn't have to be expanded. I mean, it can be any.
Here it's just a complete graph.
Here is the complete graph, but there's a distribution, so.
Yeah, I can take zero weight on any subset of the edges, and yeah. So this is not for finite general access. Yeah, this is
Can I just ask to think about the picture? How different is this from the finite field story? Do you know?
from the.
Finite field story, like GLN of FQ.
Oh.
Are experiments and you know.
No, so okay, so okay, so the only experiments I carried with GLN of a finite field were before this observation, were several years ago, and we didn't see anything. And I'm positive, even though we haven't done simulations yet, that we have the same phenomenon in GLN and FQ.
It's open for GLN?
Yeah, it's open. I mean, many things are, even in UN, it's actually open. I mean, I'm not, we don't know, we have a conjecture, we have, I'll say exactly what we know. We still, the complete analog is open. The complete conjecture is still open. So all these things are basically open. But before, I should say, I mean, what is uniformly random element in U2? This is the hard probability distribution. The natural probability distribution of these groups, which we use. And so first of all, so simulation. So we first did some simulations, and we saw like.
Sorry, you're describing a process of random walk?
No, it's not a random walk. I choose, okay, you can think about it as a random walk, but I mean, I think it's easier to think about it in the following way. I want to choose a random unitary matrix. Okay, and then evaluate it under some representation. Okay, first of all, this process just tells you how to choose a random unitary matrix in UN.
Yes.
Okay, and it's the following. I fix any probability distribution on the pairs, and then I according to this probability distribution, I choose a pair, and then I choose a hard random matrix of a 2x2 matrix, and I embed it according to the pair that I chose.
Okay, so what is a spectral gap, or the second it's eigenvalue, or?
Yeah, right. It's what. Yeah, it's what we are interested in. I mean, so.
Doron,
yeah.
Maybe even before that, like before we said, you know, any transposition, you can look at it as if you add the identity or something, you're looking at like a copy of Sim2. This is a way to like generalize one transposition, right? Like, are you going to sample several things using the same process independently, or like what's the
It's not one because I choose, I can choose any ij here. Right, so I mean, it's very similar, so. You can think about it as a graph. I have a graph on n vertices. And I have weights on every, I have a weight on every edge.
Sorry, in the end of this process, you get one matrix.
Yes, right.
So it's
You
one,
get a distribution over matrices.
sure.
You imagine the Cayley graph whose generators are from this distribution.
Yes,
Like an infinite Cayley graph with an infinite number of generators, but it's kind of simple.
I see. So, sure, so when you think about subsets, you're thinking about these probability distributions, and okay.
So what would be the what's the, if you can spell out the analogy completely? You have this infinite Cayley graph and you want to know what the spectral gap is.
Mhm.
And you're gonna check it by looking at the spectral gap of what? Just S? Just the distribution over S? That's your conjecture going to be?
No.
No.
It should come from some irreducible
Come from some
representation.
symmetric representation.
Yeah.
You have the standard representation, what else would you use, right? I mean, that's,
Mhm.
you'd use the standard representation,
Okay, I would think.
that's what you use.
That's good, yeah, good
So,
guess.
sorry, so. the
No,
conjecture-
eventually there is this huge Cayley graph with infinitely many eigenvalues.
Right, and you can map every matrix via some representation to a finite dimension, to some action on some finite dimension.
Yeah.
thing. And you're gonna evaluate the spectral gap there and hope that
Yes.
it dominates the entire.
Yes, yeah. Like the spectral gap of the infinite, the Eude process on this infinite Cayley graph
Okay.
always comes from second, but is the same as some finite some finite process or finite irreducible, finite dimensional irreducible representation. And very, I mean, and deterministically. Okay, so first of all, so simulations, they show that there is a strong phenomena. So
Doron, can you at least write formally, what do you mean by spectral gap in this context? Because this was not defined in any place. This is suddenly L2 of U2 of UN or something.
right, but okay, so I mean, I really prefer, I think it would be easier to just think about it the same. If you just thought about representations of the symmetric group. So instead of talking about the Cayley graph, what I would say is that I have a list of irreducible representations. I look at the loudest eigenvalue in each one of them. And except for the trivial one, and among all of these, there's one representation that
It is not even clear, even under this sampling process. What does it mean to evaluate it through a certain irreducible representation?
So I will-
of UN?
Yeah, so I will soon get to it, okay?
Okay. So we don't know yet what that's.
We don't know what the adjacency is.
Yeah, like.
Yeah, but I will explain. I will explain in a few minutes what it means. But the way I think it's be easier to think about it is like comparing irreducible representation. So I want to think about the others.
Yes, but the irreducible representations live in a space which is independent of this sampling mechanism. So I'm trying to, at some point.
Right, so I just look at I'm going to look at the expected value of my random element under this representation. So I sample it according to this distribution, and I look at the expected value and I map it through the representation, and I get some expected matrix, right? It's going to be an expectation over some matrices.
Expectation
Yeah.
over this distribution when I map it to GLDC through some.
Yes.
irreducible representation.
Yes. And this is really, I mean, you can think about it like that, you get the same eigenvalues. These are really the eigenvalues so okay, I don't want to, yeah, I want to get, I don't have that much time, I want to get to the really the conjecture, what we have, but I hope it will be clearer after. Yeah, after in a few minutes it will be clearer. I want to mention one important. Okay, when you think about it like that, what is special about 2? right? Before someone asked what's special about transpositions. But in fact, it seems like there's nothing special about it. And in fact, the same phenomenon. In simulations, when S is just all this is every sorry, my notation here is not which letter should I use? Okay, let's use B. Okay, in fact, I can doesn't have to be a graph. It can be any, any hypergraph on n vertices. Basically, I can do the same by embedding any I pick any subset of 1 to n, and I do the same process. Instead of looking at U2, I take UK and embed it in this way. And I get the same phenomenon. And this is what Caputo actually conjectured. Caputo conjectured the analog of this in Sn. And this is still open in this, so it seems like even in symmetrical, this is still true. You can take not just transpositions, not just pairs of elements, you can take any subsets with any probability distribution on the subsets, and then given a subset, you take a random permutation among all those that are supported on this subset, and you do the same thing. And it seems to be true, and this is the most clean conjecture that is open for the symmetrical. So with this, so what is our data? So our data is so you can think about is a weight, which we call WB for every, and you see this should be non-negative. This is for every subset of n, and our element and UB is subgroup of UN, which is, you should think about it like that. Okay, we have one on the diagonal outside the coordinates that correspond to B, and in the coordinates that correspond to B, we have a uniformly random unitary matrix, and our random element is the sum over all B of WB times U. Okay, I'm going to write it like that, but and when I say this, I mean a random element of UB. Yeah.
About the discrete conjecture.
Yeah, Caputo?
Yeah.
Yeah.
So he's saying you have some distribution over this block.
Yeah.
I don't know, maybe blocks of 3 by 3.
Hmm?
And then once you pick the block, what are you picking? You're just picking like the sum of all permutation matrices.
Yeah, we take the average, yeah. Sum of average.
It's a scalar.
No, no, I don't put the average. No.
So what?
The uniform.
I'm taking a random one uniformly. So if I have.
So is the conjecture, so the conjecture is saying that a random set chosen by this way will have, it doesn't say something about every set. It's saying something.
No. It's a very special set of distributions. So you have any distributions on the subsets and then uniform distribution within every subset.
Right.
And still the standard representation.
And still the standard representation whole. Yeah, this works, but simulations,
But
there are some partial results. yeah,
Even when B, the size of the B's is unbounded.
yes,
But my question is,
well, simulations of
Yeah.
this is a statement about something that's supposed to happen with like asymptotically almost surely or something, or
no,
asymptotically?
no.
Yeah.
What?
Okay,
There
you mean
is
is
a
many
family
group is no, you have a same graph, but
No, so I don't understand, like, where
There
is the
is a-
randomness here?
So
in
there
it?
is a family of random walks and permutation groups generated as follows. First, choose a distribution on blocks, then choose inside the block a uniformly random permutation.
Good.
This induces a random walk on permutations. The second eigenvalue of the adjacent of the Markov operator of this random walk comes from the standard.
No, I don't understand what the random walk. What are you walking on?
What?
What?
perhaps you can take
The
it,
Cayley graph.
perhaps we'll take it to the break, to the lunch, okay? I mean, I'm not going to talk about the symmetric group, I really want.
No, I understand, but this makes me kind of not understand also what's happening in the UN.
But we had two graphs, one over n factorial things and one over n things,
Sure.
and the two spectral gaps are the same. That's the statement.
This is the statement from the last hour.
That's the same, it's just the graphs are now different. The generators are more complicated, that's all.
So can I view this as like this Caputo conjecture gives like any distribution of the B's will give a distribution of the elements in the symmetrical group, and
Yeah.
then you add them together of the standard the standard representation of the regular representation, and
Yeah.
this giant matrix. You analyze the second largest eigenvalue, and you say it comes from the space of the standard.
Yes, exactly.
Okay, that is really.
It's not.
Okay, so,
Maybe I'll ask.
yeah, I really want to go to the, to what we think is the conjecture. So first of all, okay, so the EREPs. Yeah, I hope I will show you some concrete example, I think it will, of what are the eigenvalues you get. So the EREPs of UN. So remember, SN was classified by Young diagrams. EREPs of UN, they're classified by highest weight vectors, and these are the vectors that look like that. Okay, lambda 1 is not good. New one. UN. They're all integers. And they're non-decreasing. Okay, so they are classified by high squared vectors. So you see there are infinitely many of them for every n. And importantly, I mean, we don't really have to understand exactly how to construct them. It's enough to know the following fact, that each one of them is contained in RKL for some non-negative integers, well, RKL, this is my notation. This is the following representation of the unitary group. You take the matrix A and you map it to the the tensor power, K tensor power of A, tensor with the L tensor power of the conjugate. So, give you some examples. So, okay, R10, this is the standard representation. It's a defining representation, it takes just every matrix to itself. And it corresponds, this is irreducible in this case. And it corresponds to the highest weight vector. One with many zeros. The second one is so R20. So this is already reducible. And so this is n factorial, n squared dimensional, right? And this is a sum of two of them, it's sum of 2, 0, 0, 0. Okay, I want to give two more examples. This is 1, 1. It all decomposes to 1, 0, minus 1 plus zeros.
What do these vectors of numbers mean to us?
For now, just classification. Just a way to name any, these are just names for the irreducible representations for now,
Right.
okay?
But at least 0, 0, 0 is a trivial.
Yeah, this is the trivial one. And this is now, you know, this is now the standard run, just taking the matrix into itself. Here, I mean, you can, once I give you this fact, you can reconstruct this representation by finding, I mean, I told you that this is very specific, and I told you what is the decomposition. You just need to find some vector which is invariant, which invariant under all the matrices, and this will give you the trivial one, and then you take the orthogonal subspace, and it will give you this representation. Okay, in general, it's more complicated, but and here's the last one I want to give is output 2. So this is A times A times A conjugate, and this is, okay, not sure I have the time to write it, but okay, it's
You have plenty of time.
yeah, this plus this plus this plus 4 times. Yeah, 4 times plus 2 times Liggett. Okay, from these examples, I think you can perhaps guess which representations, which of these sequences of numbers appear in every RKL, perhaps or not. I mean, well, I could give you perhaps a few more examples. I mean, there are some very easy rules, combinatorial rules for which representations appear in which RKL, but it doesn't really matter. But okay, so let's go on to what is the so how do I compute this spectrum of all these matrices, of all these representations? Okay, so I plan to do it today, but I'll do it next time. So it follows from some. Okay. Okay, so let's start with Alon's guess. Okay, I mean, the question is which element dominate, right? So this is the question. I want to generalize the Aldous conjecture. What is the analog of the standard representation in the symmetric? And the first guess is what Alon suggested, I think. The standard of UN, namely R1 and 0 or this one, which just takes A to itself. Okay, but let's see. I mean, if I take what is so to understand what is the spectrum of this under this representation, what I do is I take the expectation. Should I write expectations or integrals?
Expectations.
Expectations? Okay, you're very deterministic. Okay.
No randomness in the answer.
Yeah, okay, so let's so I want to take, for example, if I just have, I look at the first, let's say my S is 1, 2. And so I want to take a random matrix that looks like that. Right? How random unitary matrix in U2 that I think about it as that, as like that, embedded inside UN. And I want to take the expectation of A as a matrix, because this is the representation. If I want to use another representation, I would put here A tensor A, for example. Okay, this is the way you compute the eigenvalues. Okay, so for this I need to understand what is the I mean, of course I get, I mean, here I have some 2x2 matrix, 2x2 block. Everything else is 1s and 0 because these are constant eigenvalues, constant entries. And here, so these are effects that I will prove next time. Just mention the facts quickly. So the expected value in UK of Aij just 0, and the expected value of so if I take this product, I get so if Ij is the same as KL. Okay, it's not the same K. Sorry about that. I mean, same K as this one. I get 1 over K, and otherwise I get 0. Okay, let's just use these two facts. I will explain them next time. Okay, so what do I get here? What is the expectation? What do I get in this block?
0.
Zeros, right? Each entry individually, the expectation is 0.
Don't I need to be orthogonal to something and subtract identity or something like that?
You don't need to.
Don't you need to be orthogonal to some invariant vector here and therefore subtract?
No, because no, this is an irreducible representation. There is no, yeah. Again, you can show pretty easily that if you start with any non-zero vector of order of size n,
You go anywhere.
you can get anywhere by
By the way, you choose this entry 1 and 2 based on some distribution.
Yeah, I'm just showing the example of 1, 2. Yeah.
Like deterministic is like a
Yeah, so this will, so basically, I mean, overall, if I get, so I have a sum of weights, right? So what will be the final, so yeah, I should give it some name. Okay. Yeah, let's call this, I don't know. Can you help me? No?
I don't know what would be
No, I just want a name. So overall, what do I get overall?
I want
What do I get if I take this random element and look at the expectation, right? So you see from here, I get zeros, I get, I'll just write it down, then you be clear. What I get here, I get 1 in the first coordinate, only when the first coordinate is not, doesn't belong to my set. So I get the sum over all weights, where 1 is not in B. And here the sum of all weights where 2 is not in B, and so on. So it's a very simple calculation given these facts. This is what I get. These are the eigenvalues, and of course I can derive from here the largest eigenvalue. Okay. And we're even able to prove, so from A, this is an easy theorem, that in fact R10 always dominates RKL if K is different from L. So we can actually show this is relatively easy. This actually dominates. The largest eigenvalue here is larger, for example, always larger than, for example, the eigenvalue here, when I take A tensor A. Or not with these two. These two are balanced, 1, 1, 2, 2, but it's always larger, at least as large as this one. But it always dominated by R11. Okay, so this is not this guess is not the. I mean, you probably saw it in simulation before you prove it, but actually you can show, and I will show it next week, that R11 always dominates. So let's look at R11.
When you say contained, it's also dominated? You said each one is contained in RKL. If it's contained, means it's also dominated by it?
No. I'm saying RKL is reducible, so you can decompose it into reducible representations. You get you find.
Okay.
I mean, each one of them can be found in infinitely many RKLs, but.
No, then ask if you say it's dominated by this, then can you say it's every other is also dominated?
I'm saying that out of.
Dominates every RKL
And therefore it dominates each one of the irreducible representations that appear in the composition. Yeah. So 1, 0, 0, 0, 0 dominates this representation and dominates this representation. Okay. So it is somewhere high in the level of in the grading of representations. Okay, so it's always okay. So perhaps this is our second guess.
Wait, but R11 contains the trivial values.
Right. So I mean outside, yeah, good point. Yeah, so I forget about the trivial.
Okay.
Right? Yeah. So I mean
modding out the trivial.
Yeah, let's say 1, 0. By this. Okay. And second guess is this one. Okay. I'll just tell you very, very quickly. So if you do, so we can use this fact that I said before, and we can compute. I'll do it next time. With more slowly, but what we get is, for example, if I take again U12, so again this I take the expectation of what you see. So we have an n by n matrix, and if I do it in the right basis. I'm going to get here a block that an n by n block. It looks like that. And here I'm going to have to be like something like that. Okay, these are 1/2. Okay, does it look familiar?
Like everything else are zeros?
Here I have zeros, perhaps I will enlarge it. So this block,
That's the over commutation.
yeah,
You mean all ones in the bottom?
yeah, this is diagonal. Here I have some ones, some zeros. Basically, okay, so it's, I mean, this part is dominated, I get this, again, block matrix inside this representation. So it's a finer decomposition to blocks than what is suggested by the reducible representations. This block is not interested, it's actually dominated again by the standard one, by the sum of weights. But this block is interesting because, like Michael said, it's exactly what I get for permutations, for the average on these two permutations. And this is, so in fact, we see that the largest eigenvalue is in fact is the same as largest of the standard of Sm. So we can actually see the eigenvalue of n that is the largest one in this new problem. So, right, it's okay, it's really nice. So it must be this the ruling, the dominating representation. And we thought this is what we thought for several months until we discovered, and it also in simulations, but eventually we discovered that our simulations were too random. And if you choose, so we just took random weights, and it turns out that if you take the weights, if they're actually equal, or at least very or close to being equal, you get something different. And so I just end by stating the conjecture. That in fact the winner is this one. And by the way, it contains, right? You see, it contains the previous representation. It also contains this one. So for any set of weights, the largest non-trivial error comes from
But I don't know which one of these.
So I mean, there are cases. I mean, I don't have a full classification of when it's this one and when it's the other, but it's always conjecturally it's always one of them, and and we prove it for. So there are two main cases. One is when all the weights are the hypergraph is basically on only when the size of the step sets is n-1, or when the weight is only a function of the size. So it's like a this is closer to the Koenig-Shahani, right? I mean, the weights are for all the pairs. I have the same weights for all the triples. I have the same weights. And perhaps another theorem is that you can see all the eigenvalues the symmetrical, if you use the same ways for the symmetrical, they always appear. So in a sense, this conjecture is stronger than Caputo. It contains Caputo in a sense. And there is a nice model, nice process of size and square, which captures the spectral gap. So this is the analog of the graph, like one particle. There is a process, which I will define next week, which captures the graph, the highest eigenvalue. So this is again, this is conjecturally in general, but it's true in these two cases. Okay, so yeah, I originally planned to do it solo, but we have it next time.
Okay, thanks for a wonderful first lecture. Huh? Give some intuition why n squared is already enough. Well, we already.
I mean, it's basically, you see it here. So this is an n squared dimensional representation, even if you subtract the one, it's of order n squared. But there are these blocks inside. So unlike in the symmetrical group where the transpositions generate, if a block is invariant under all transpositions, it is an irreducible representation. But here, because we take these averages, there is a finer decomposition to blocks. It's more finer than just irreducible representation. So like here, you see we have an n by n block. Even though this is an n squared on n square matrix, we have a small block. So the same happens. I'm not sure it gives an intuition, but yeah, the same happens here with this. This is an n to the fourth matrix, but there are blocks inside, and the block that matters is only of size n squared.
But why having a small block of n by n should indicate that this would go in?
No, it doesn't indicate, but just I mean, just in this example, I mean, yeah, I mean, this is next week you'll see this is clearly dominated by the other one, and this one is the one that I don't know. It's just an example. It's not an intuition.
So next week you'll give a proof outline of some of these theorems.
Yes.
And you also mentioned the proof.
Yeah. So I may. Yeah, I may also give an outline of the proof of the original Aldous conjecture.
These are related, like the outlines are.
There is some relation with I mean, at least the parts that we use branching laws of representations. What happens for representation when you move from Sn to Sn minus one, or from Un to Un minus one? These kind of arguments appear in both proofs, but.
Are there any questions? Okay. So let's do.